very different if I come to a place and there's no snow in the winter. So this is a shorter version of what I had 3.5 hours to cover yesterday. So it's an introduction to the realm of the fungi in the soil and a little bit other biology besides that. So the launching point is really that word, mycorrhizal. Greek roots of this word, myco is the fungal kingdom, rhiza is the root of plants. And while there are mycorrhizal fungi in the dormant stage, as spores and as hyphae and root fragments, you don't have an actual mycorrhiza until you have the union of the two. So you gotta have the plant piece to have the fungal piece to be active. And together they do some amazing things. So this is just one part of the whole soil food web. And here we're talking about the bacteria and the saprotrophic fungi and the actinomycetes that decompose organic matter, and they in turn get eaten by nematodes and protozoa, and they release mineralization that the plant can take up, and then we get into the arthropods and the earthworms and what have you. And my perspective is that this is my team in my orchard, on my farm. It's your team too. And because we're human beings, we'll be a little bit arrogant and we'll say, we're the captain of this incredible team. In saying that, just be really tuned into one thing. You have one job as a captain, and that's not to screw up your team. This is a picture of the nutrient transfer mechanisms, fungi actually penetrating into the root cell. These are called arbuscules. And when you look at that, my eye sees a tree, because I'm kind of a tree guy. You might think that looks a lot like the feeder root system of a plant. If you've been trained medically, you might think that looks a lot like the alveoli in our lungs where oxygen gets exchanged. So I'm a guy who's married to a Kansas woman who is an herbalist. And one of the traditions in herbalism is known as the doctrine of signatures. And in that way of thinking, you look at a plant, how it grows, the way the shape of leaf is, and it suggests something that this might be a medicinal use for this plant. When I look at these arbuscules and think about trees and feeder root systems and the exchange of oxygen, it's like, this is an essential link to life on this planet. So all sorts of things happen when plants have this affiliation with the fungi, starting with the core idea that when good guys occupy a niche, the root, then there's no room for the bad guys, the pathogens. I'm going to talk about how I, as a lone plant, have an ability to work with my plant community to get a whole lot more nutrients in balanced form. That in turn abets healthy plant metabolism. I'm going to take a quick look at what I mean by that. Through the fungi, plants in the community can communicate to each other. It's the underground internet. It's much better than ours. We're going to look at how fungal presence induces systemic resistance to disease, so strengthening that metabolic response. And all those things added up, that's where ecosystem resiliency comes from. So when we talk about drought and hot summers and flooding, this whole ecosystem is buffered in part by having this fungal connection. And then there's one last little thing. Fungi, mycorrhizal fungi in particular, are responsible for getting approximately 40% of the carbon down into the soil. It's not that little, it's very important. So some 450 million years ago, when the oceans receded and land appeared, in the tidal pools were the ancestors of what would become vascular plants. Think algae. And those ancestors of plants didn't have roots. And in the same tidal pools were oceanic fungi, which had filamentous hyphae to absorb nutrients. And they made a surrogate deal where the fungi essentially served as the root system until plants went on to develop their own roots. And every plant began with this affiliation. Some plants have, along the way, changed their mind, but they have the capability of going back if conditions are right. But just to establish, every some 95% of the plants on our planet, the crops that we're growing, desire this affiliation with mycorrhizal fungi. So let's just learn a little bit about some of the types of mycorrhizal fungi. The ectomycorrhizae don't actually penetrate into the root cells. These are fungi that evolved from decomposition wood fungi, rotting fungi. But what's special about them, and I'm going to point out why, is they have long explorer hyphae. They can reach as much as 12 feet away from the plant. So that increases your ability to get nutrients that otherwise are too distant. And the endotype, ENDO, that means they're the ones that penetrate into the root. That's the ones that we're all working with whatever kind of farming we're doing. They don't so much have a distant hyphae, but they have a much denser mycelium right around the root. So the ectotypes are affiliated with trees of the forest. And these are ones you can see with the naked eye. This is the fungi that we as humans first noticed back around the time of the Civil War, and it took a long time to catch on to what they were doing. These are the fungi that have mushrooms, fruiting bodies that come above the soil. So if you've gathered chanterelles or boletes or matsusakis, you're dealing with a mycorrhizal mushroom affiliated with a certain tree, and if you're a good mushroom hunter, you actually learn to look up before you look down, because it's the type of tree that's going to be an indicator in that respect. Those long explorer hyphae have the ability to mine minerals from rock, and I'm going to look at how that happens. So, as a lone plant, if my arm was a feeder root, and I was a endotyped plant, so wheat, or legume, or corn, or the soybean, or the apple tree, by myself, I would be able to absorb soluble ion nutrition approximately 3/4 to an inch away from my surface as a root. And that's by virtue of the fact that groundwater through capillary action is bringing me that nutrition. Now when an endomycorrhizal fungi works with me in a collaborative manner, I now have a mycelium that's 4 to 6 inches surrounding me as a root. And so I now can access a lot more root volume than I otherwise could. And the issue here is that roots by themselves often end up in a nutrient depletion zone, whereas with the fungi, they start to have access to more nutrients. Now, it took us some 50, 60 years to kind of deal with the fact that this microbe, this fungi, wasn't a disease. And it wouldn't be until the 1950s that actual research into mycorrhizal fungi and what they do kind of came into being. Back in 1924, Rudolf Steiner, a German man, gave a series of lectures that became the basis of biodynamic farming. And at that time, we talked about this regular mesh of roots and how they worked together, and it would almost become like a common root beam. So people didn't really know about this, but he had this sense of like how to describe it. I like this word, common root beam. Today, the scientists refer to this as a common mycorrhizal network. So I want to get you to appreciate more what this means. So we're going to become a plant community right now. And I'm going to be an apple tree. You can be whatever you want to be, but I do want some of you to be corn and some of you to be grass and legumes, and I want some shrubs, some willows and alders, and we have a diverse mixed ecosystem. And as a common mycorrhizal network, a few things happen. I, as an apple tree, will have multiple affiliations with different fungi. You, as clover, or you over here as blue stem grass, will have multiple affiliations, and we might share some. And because we share some, we're now connected. And not so much like I can reach with my roots and fungi 100 feet away, but there's a series of plants between us that connect us. And in turn, a different fungal system that I'm maybe not connected with is working with other plants, but some of them are in the group that I'm connected with. And suddenly, through that connection, this is how nutrients can start to move. And now, rather than just 4 to 6 inches around me, I have fungal networking, root networking, and nutrients are now being spread throughout our community. And the mycorrhizal fungi, some species that have the ability to move water. There's some that are zinc specialists. There's some that are really good at starting up in cool soils in the spring. So we really want a diversity to make this magic happen in what is known as the common mycorrhizal network. So let's learn a little bit about this other group, the endomycorrhizae. These are invisible. Probably about 85% of plants. Like I said, it's everything we're working with. You start thinking about nutrient balance and the delivery of trace minerals and what have you to you as a plant, well then you're very likely growing more nutrient-dense food and produce. The fact that the network stimulates induced systemic resistance, but also there's a signaling that takes place. Helps me prepare for disease and insect happenings. And just an example of that is, let's say over in that far corner of our community, there's some sorghum. And sugarcane aphids come on the scene. And so the sorghum plants over there have a certain phytochemical response to try to get rid of the aphids. But through their roots, there's another phytochemical signal that goes out. And that reaches us over here. And we don't then develop phytochemicals to resist aphids. What we do is that prompt gets us as plants to send out volatiles that tell beneficial insects, come here because aphids are coming. Maybe aphids are coming. So that's just an example of how this works. And again, it's about the interconnection of plants, what I call passage plants, that ties things together. Another part of thinking about this is that it's through our shared protoplasm. So when a fungi penetrates a root cell, it's in the sap of that plant. And when over here, another part of the root system is penetrated by a different fungi, it's in the sap of that plant. And that's the medium where things can be exchanged. So the fungi are getting carbon sugar energy from the plants because they're the ones who can photosynthesize. But they're using that carbon currency. In turn, they're trading with the plants with minerals, but they're also using that with other microbes to accomplish certain tasks. So fungi carry forward in primarily 3 ways. One is just the fact that it's the growing season and the hyphae are reaching, and now we discover a plant that's part of the fold. And another part of the storyline is the fact that fungi of the same species can fuse together. They can graft. It's called anastomosis. And that allows the fungal network to form more efficient, effective pipelines throughout the common mycorrhizal network. The growing season ends, or the crop is harvested, it's gone to seed, what have you, and the roots remain in the soil. So there's corn roots, there's soybean roots, the roots of any of your garden plants, mostly, not the brassicas. The hyphae live in those dead root systems for as much as 6 months, and they're living off the fats that were stored in the roots. So when you're not tilling and tearing up the roots, not only are you not tearing up the mycelium, but because you're preserving those root fragments, you're helping the fungal aspect carry forward. And then finally, fungi have spores. So these are the reproductive bodies which lie in the soil dormant until they encounter a root and the whole connection begins. So let's understand a little bit more about those spores. This is a poisonous pigskin puffball. So I can see it. It's on the surface. This is affiliated with certain trees. And this puffball, when it has those spores, when it's ripe, so to speak, and breaks open, you can see those clouds of that puffing release of spores. They're spores that are meant to travel in the end, in the wind. They have little hairs. They're spores that can deal with being out in the sunlight. These are the ectotypes. So that's a great skill set to have. After a forest fire, spores in the wind can come back and affiliate with the little trees that are recovering where that forest fire took place. On the other hand, endotypes, the types we're mostly working with, They move around in the guts of earthworms on the back of a burrowing mammal. It's not so fast. They're not a type of spore that blows in the wind. They're not a type of spore that deal with sunlight very well. They're an underground reproductive spore of the endomycorrhizal fungal types. And just so we understand this even a little bit better, in 1980, when Mount St. Helens blew up, approximately 250 some miles were subject to this heat blast of 660 degrees Fahrenheit. And it killed the plants, and it killed the biology in the upper inches of the soil. And it wouldn't be until 20 years later that both plant life and fungal diversity got back into the heart of that blast zone. So what I'm establishing right now is that with the endotypes in a very degraded soil, it can take a long time for it to be recovered. In a very, very degraded soil, the mycorrhizal presence can actually be extinct. So we're going to somewhat talk through the scenarios of where it might be worth making sure that inoculum aspect is restored. And we can do that, in part, because it's possible to concentrate those spores and have inoculum of specific species in a commercial product. There's also a homegrown way to go about this, in that things like the grasses have many multiple affiliations. So in something like annual ryegrass or Baha'i grass is grown in a sack, and it was inoculated maybe with indigenous mycorrhizal fungi that you gathered from soil nearby, or even a commercial product because you wanted to be sure of having a certain species that you were going to be populating. You can use the soil and root fragments in that sack. So there's different ways to go about it. But the key thing that I want to point out with these products is that you really want to get one that A, specifies which species of fungi are there, and not so much because you need to know those names or any details about it, but because that's the way you know there's 9 species, or 7 species, or 4 species, versus inoculum products that have 1. So these 3 I listed here on the screen, mycorrhizal applications, bioorganics, and root rescue, which is up in Canada, they're the 3 companies I know of that have not. There's other reputable products, and 4 is a basic starting point. But those that have just 1, you're not really getting the same amount of diversity that you want. So in a given healthy, undisturbed ecosystem, there will be as many as 20 to 50 species of fungi at play. And the more diversity here, the more the network is complex and able to do more amazing things. And I've already spoken about how different fungi have specialties. Most of the fungi are really good at getting phosphorus, but they need a teammate. We're going to look at that. So the names of the core 4, again, it's not so much important that you know this, but they've been selected because there's worldwide some 300 to 400 species of endomycorrhizal fungi. There's no fruiting body. They reproduce asexually. And so they have not created untold amounts of new genetic diversity. It's like nature nailed it in the beginning, and those species have carried forward. And Glomus interradices has the smallest spore of all of them. So those products that only have 1, they have a really good species they're using, but they'll make this claim that we have 6 times the spore count than our competitors. That's because they only have the 1 type of spore. And that's what we want to get a little bit more diverse. Glomus mossi is one of those that's really good at moving water. So these were selected because they specifically covered a wide range of skill sets, applicable to sandy soils, applicable to clay soils. The one I highlighted here is enzyme activity increases access to micronutrient uptake. But when we talk about healthy plant metabolism, we're going to be stressing the importance of trace minerals. And when it's delivered by the biology, it comes in a form that the plant can use. So something like that last column, Glomus tunicata, which is one of those 4, is is a fungi that we've done studies and shown it has this skill set. So again, that's why this mix has been selected, is a good overall skill set at play. So another aspect of this is that the root needs to signal through phytochemistry, through, well, root chemistry, flavonoid chemistry to be more precise, the spore to germinate, just like a seed has to germinate. And a little hyphae develops out of that spore, and it requires certain draw signals from the plant to go in this direction, go in this direction, because the root's over here. But that root has to be really, really close to that spore. And so when you start to think about the randomness of all this, and just getting some spore powder in the soil, or the earthworms delivering it, your crop doesn't necessarily find it. Back to me being an apple tree, this is a good thing to understand. I have a root system that's probably about 2.5 times the diameter of what you see here for a canopy. So now just imagine me and my roots down below. But even with that extensive root system that a tree has, I'm only accessing like 3% of the soil volume that I'm in. And again, this is why this mycelium ability to bring nutrients is really, really important. So getting close to the root has real relevance. You know, that might look like, in my case, with a bare root apple tree, I dip it into a hydrogel formulation of mycorrhizal spores. I can't see the spores, but I can see the hydrogel, and it always makes me feel like I'm doing something here. But you know, if you're planting corn and you feel there's a need that justifies inoculating, you might consider a seed treatment. You can mix the liquid formulation in the furrow application of fertilizer, if you're using fertilizer, or in a 2x2 placement. But all three of those suggestions are getting the spores in the vicinity of that root system. As it develops, it'll find those spores. So also another thing here is this world of fungi is very adaptable. And there's no hard and fast rules that you as a wheat plant have just 3 friends, or you as a wheat plant have just 1 friend. And in truth, things are in flux. There's a real ebb and flow to this. And I mentioned how the same fungal species are found across the world. Here I'm talking about a tropical ecosystem, a savanna ecosystem, the grassland ecosystem, the temperate forest ecosystem, the boreal forest. It's the same species. When inoculum is introduced into a indigenous microbe scene, some of those fungi may not work with the plant that you're growing. Again, there's a little hit or miss to it. With the core 4, generally assume all 4 are going to be active with most crops. But another thing that happens is if the Glamis massae in that spore product, let's say it came from the southwest, it develops certain skill sets to deal with that more arid environment. And when it's inoculated on a plant and it meets Glamis massae that's already in your soil, and this really ties a lot to the degree of disturbance of what's the history of the plant. Because they're the same species, they can fuse together, but now that skill set from the southwest is introduced to the native species of Glamis massae. So now we're spreading the skill sets. I'm often asked this idea of indigenous microbes versus foreigners. One, I just want to establish they're probably not foreigners, and they might have a set of skill sets that can help overall. But we'll look at, well, here's a scenario. Canola. Some of you grow a plant that is considered to be non-mycorrhizal. So I say that with a grain of salt because it's actually very adaptable. And in some situations, people think their canola has this affiliation going on. But when you spend a growing season with a non-mycorrhizal plant, you have not utilized those root fragments. That's gone, it's passed, and you've not generated spore connections. So some of the spores get lost just in the process of microbe-eating microbe and things near the surface of the soil, it overheats, and you don't have quite as much mycorrhizal oomph remaining in that soil. There'd still be some. Again, this really relates to the history and how much tillage and all that has been taking place. But that's one of those scenarios where maybe coming in, it's worth considering inoculating corn, because corn really has a strong affiliation with the fungi, and that's a key part to understand how different plants have this dependence on being affiliated. This whole evolution across biological kingdoms, pointing to collaboration and support networks as the way to proceed in life. Back in the day of Rachel Carson, who wrote Silent Spring, there was an ecologist, Frank Edler, and he said something like this: nature is not more complicated than we think. Nature is more complicated than we can think. And I'm kind of cool with that. I'm also aware that we as humans are at best in kindergarten in terms of understanding this realm of the fungi and soil bacteria and how plants communicate with each other. I mean, it's just awesome. It's just amazing. I respect it and honor it, but I mostly don't know it. So this idea of mechanisms of nutrient exchange, the idea that a fungus can actually penetrate into a root cell and form that harvestule. You know, the plant and the fungus have cooperated because the usual signal to repel a microbe penetrating the cell has been toned down to allow this collaboration to proceed. But there's a real gift that happens as a result of that arbuscule being in an individual plant cell. And that gift is this: each arbuscule lives on the order of 3 to 7 days. And then it's done its job. It's been stretched to the maximum. And it is cut off from the mycelium, the hyphae, that's called hypholysis. It's cut off from the connection with the fungus. And whatever nutrients are in that arbuscule go back into the sap of the plant. And here we're talking about some complex nutrition. Things like structural cell wall proteins, acidic polysaccharides, lipids. Complex food, we're going to learn in just a little bit, has a lot to do with helping plant metabolism go all the way. And this is the gift of the fungi to the plant. Let's understand a little bit about the bacterial side. So bacteria, their primary highway in the soil is moving along the hyphae of fungus. That also gives them a spot where bacteria can transfer genes and adapt to soil conditions and become more of a profound presence in that soil. But there's more than that going on. The fact that bacteria congregate towards the tips of the fungal hyphae is an opportunity for another collaboration to take place. And it works like this. The fungus is taking carbon, sugar, energy from the plant, and some of that is exuded through the hyphal tip. And that in turn flows back and feeds the bacteria that are along the hyphal length, which allows them to live and thrive in that place. They produce organic acids, and this is the means by which ectomycorrhizae dissolve bedrock, and in turn take minerals back up through the hyphal system to the plant and to the surface of the soil. So this is nature's way of remineralizing the soil. Another example of that same length of hyphae now we're talking endomycorrhizal hyphae, has a group of bacteria. One example would be the phosphorus solubilizing bacteria. And they're taking that carbon energy, producing organic acids to dissolve the phosphate rock in the soil. And that's why almost every endomycorrhizal fungi has a skill set to bring phosphorus to the plant. They don't do it alone. It is a collaboration. It actually looks like this, but this is my one X-rated photo. And one we won't dwell on. But you get this idea of how we've got some teamwork going on here. It gets even cooler with bacteria. Just like mycorrhizal mycorrhizal fungi penetrate into the root cells. Many different strains of bacteria and also singular cellular fungi, the yeast groups, can actually be transported inside the feeder root tip, where they give up nutrients to the plant, kind of like that hypholysis. But they're not gone. They are then exuded back out into the soil environment where they resupply their nutrients. So this is, again, a mechanism of complex nutrition, where bacteria can deliver amino acids to the plant. You know, this back to something Rudolf Steiner said. And again, 1924, this person was perceiving this. There's absolutely no hard and fast line between the life within the plant and the life of the surrounding soil in which it is living. It's only in the last 10, 20 years our limited understanding has reached the point where we're seeing how this penetration, this sharing of complex nutrition is taking place. So let's look a little bit at the plant side of all this. And this is a quick summary of, if you go listen to John Kempf, you're going to hear a lot more details, but just a quick summary of what's taking place in terms of plant metabolism. So plants are out there in the sunshine. It's either a sunny day or it's a rainy day. It seems like we have much influence there. Nitrogen is taken up. That's either coming because by virtue of rhizobacteria and legumes in the plant community, or microbe eating microbe, and nitrogen being released as ammonium, and also those amino acids being taken in through the bacteria. That nitrogen, in turn, wherever it came from, is combined with the plant sugars to create proteins. And plants go beyond there to create fat energy. They create lipids, fatty acids, that are the building blocks of lipids, and waxes. And we'll look at what that's doing. And if metabolism is really robust, and we want it to be, plants reach the final phase where they produce what are called secondary plant metabolites. I like to use the term resistance metabolites, which are basically the phytochemistry, the immune function of plants to ward off disease and higher order insects. So with photosynthesis, sure, the sun shines as much as it does. We might plant our corn in such a way so that we maximize the edge effect. There's things we can do like that. But it really comes down to the availability of certain trace minerals, because they act as components of enzymes which help facilitate speeding up the metabolic process. And so what I'm basically saying is if the trace minerals are there, the plant has the ability to make more plant sugars to trade with the fungi. So photosynthesis by itself, without really getting involved with stewarding these connections, probably operates somewhere at 15 to 25%. But when we work with the plants understanding this, and we create a fungal ecosystem delivering minerals, that photosynthesis rate goes up. And we go from a sluggish situation to a robust situation. On the protein front, the nitrogen is introduced. And again, this metabolism is facilitated by enzyme cofactors, talking about those same trace minerals. And this is where sugar and nitrogen come together. That forms an amino acid. A few amino acids combine, that forms a peptide. And if this protein synthesis is really robust, most of that, if not all of that, becomes complete proteins, which means that instead of having a sap that is rich in simple sugars and free-floating amino acids, that's what foliar insect pests feed off of. That's what pathogenic fungi, the ones that cause spotting diseases like apple scab or any of the rusts or powdery mildew, feed off of. And when there's less of that, you have this healthy plant where you don't see the disease thing going on. So that part of what's taking place here is when those complete proteins are formed, a cell has an outer wall, the epidermic cell wall, and inside that is a cell membrane. And that cell membrane is a phospholipid bilayer. And complete proteins are stored in that phospholipid bilayer, which means they're not available to the feeding pest or the disease organism. And one of the things that always blows my mind is how nature repeats beneficial patterns. And as you start to get into this concept of thinking about the fungi, what role do they play on this life on our planet, that fungal mycelium in the top inches of the soil worldwide, that's the cell membrane of the earth. It's much the same beauty, different scale going on. So fat energy. Essential oils will deter insect interest. The lipid reserves that are stored in the stem and in the leaf, the plant can call upon that organic chemistry, break it back down into fatty acids, back down into the building blocks of proteins, amino acids, so that it has enough energy to get through those rainy day periods when fungal disease is more likely. That's really important to me as an apple grower, because there are a number of different fungal diseases that come at different points in the season, and I really want to be growing fat apple trees. That's the way I look at it. Another thing that's happening is fats are transposed out into the surface of the leaf where they form a cuticle. So these wax crystals, I forget what picture this is from what plant, but it's fascinating when you look at microscopic pictures, because every plant species has like its own type of cuticle. It's like every snowflake is different. Every cuticle is different. Again, we don't see this. All I can do to experience this is take my apple, spit on it, rub it on my shoulder, and it shines. That's the natural waxes. Those waxes are there. They're helping hold water in the plant. They're also forming the first line of defense against certain disease organisms that have to punch through that. So when metabolism is robust, that wax layer, the reserve energy of lipids, can be 3 to 4 times higher than when things just proceed in sluggish fashion. So you're getting this idea now of where does plant health come from. And then finally, plants are producing these phytocompounds, these terpenoids and flavonoids, which are basically the immune function of the plant. They're producing alkaloids, which are bitter and for the feeding of higher order insects. This is what my wife Nancy, who's an herbalist, she gets all excited about terpenoids and flavonoids and these phenol compounds, because that's medicine that our bodies also know how to work. So one of the takeaways here is this notion that when plants get their nutrients in a more partially built, complex form, think of this as like nutrient-dense foods for plants, they're going to really thrive and have robust metabolism. When they get their nutrients primarily as soluble ions, NPK fertilization, that way of thinking, that's like junk food. And they don't do as well. So it's the real simple level. And in one sense, we could consider the predigestion of the microbiome in the soil similar to the rumen of a cow, similar to the microbiome in our own stomach. Now, this idea of reserve energy. Another aspect that's interesting is when that nematode or that protozoa eats a bacteria. That in turn means some waste products are given off, and nitrogen is given off in the form of ammonia. Well, in a bacterial-dominated soil, there is going to be a higher presence of nitrifying bacteria that take that ammonium and convert it to nitrate. The plant, in turn, can take that in. We all know that. But the plant has to convert the nitrate to other forms in order to form those amino acids. And so it uses energy to do that. And when you have a fungal-dominated soil, in terms of the biomass, fungi to bacteria, it's a more acidic rhizosphere, which results in less nitrifying bacteria. And so the plant doesn't have to do that transposing of nitrogen into a different form. As I explain a lot of these things to people, some of us get excited about the details, but I also want you to understand, yeah, I heard all this, but coming out here was mineralization, fungal connection, mineralization, fungal connection. That's what your goal is as a grower, to achieve, to help, to assist, to abet. And it really begins with a fungal ascendancy in the soil. So another look at fungi. In the fungal kingdom, we've been talking about the mycorrhizal fungi, both endo and ecto types. There are also the decomposers, the sapotrophic fungi, the ones that break down organic matter. We want them too. I mean, that's a big part of how nutrients get made available to microbes and thus to plants. There's also the fungi that live on the surface of the plants. So there's the yeasts. There are endophytic fungi that actually, and this is true in every plant, live within the cambium cells of the leaf and the stalk and the stem. And we'll come back to them. And then finally, that bottom grouping, the parasitic and pathogenic fungi, the ones that cause disease. We have directed for the last 100+ years our attention on that bottom group. And so when we spray fungicides, we don't just target that bottom group. We have an impact and effect on all these other symbiotic organisms that want to, for the most part, are going to do good for plants. So let's just take a very brief look at the disease side of this. There's, every pathogen has its own strategy of how it's going to penetrate into that root cell. It produces enzymes, and there's effector proteins and all that. But it's also the case, rust diseases I want to specifically talk about, that it isn't so much the phytochemistry that's the first line of defense. It isn't so much that cuticle layer, but its allies in place. So what you see in this picture is a rust spore that has landed on the underside of the leaf, and this is true of all the rust diseases. And rather than an enzyme strategy to punch its way in, it just goes through the open door. The open door being the stomate, the respiratory cell on the underside of leaves of plants, which is pretty clever. But we change the conditions of that when we start to understand that if there's a lot of friendly microbes on the surface of a plant, that in turn is another line of defense against plant diseases. So here's a picture of the stomata. And here there's some Pseudomonas bacillus type bacteria. The ones that have little white strands are yeast. But when we start to build that colonization up to the order of 70%, that's what rebuffs disease. And for me as an apple grower, that's a really important piece, this notion of biology on the upper portion of the plant. I call it the arboreal food web. So we've learned a little bit about disease. We've learned about some of the advantages of the fungal connection. So as growers, another really useful way of looking at all this is to start thinking about that pest, that disease, as really, in truth, a biological or nutritional deficiency. Something needs to be corrected there. Something needs to be tweaked. Because this system hums really well in and of itself. When we build up that biology in the soil, all these things start to take place. So a plant, just a real quick look at what I call green immune function, that phytochemistry. There's really two legs to it. And just like we have an innate and an adaptive aspect of our own immune system, with our red blood cells and lymphocytes, plants have that innate and adaptive aspect. And the innate aspect is called systemic acquired resistance. And that just means that a plant subject to environmental reality is going to produce a certain set of phytochemicals to resist that disease organism. This is known as systemic acquired resistance. And so if a crop is treated with fungicides on a regular basis and never undergoes this, so in apple orchards that's pretty common, that means that the chemicals produced by systemic acquired resistance aren't in that apple. And some of those chemicals are what we evolved with as a species to ward off our own degenerative disease. So the produce is now it's not just a question of less nutrient dense, but less phytomedicine that our bodies use. The other leg is known as induced systemic resistance. And this is something that we can get involved in a positive way. And going about this is all about all these subtleties in the soil that I'm talking about in terms of fungal connection being in place. But here I'm talking about two things. That presence of mycorrhizal fungi penetrating in the cell. I mentioned how it does kind of, let's say, jog the plant's memory of the idea that maybe I should produce some phytochemical and resist this. It starts that process. Well, that induces a systemic response. And then there's also things that can be either applied to the plant surface or come down in the rain through the atmosphere. So biologically induced immunity, mycorrhizal fungi penetrating those cells, that's really important. Plants that don't have this affiliation, well, that's where we're getting into that agriculture where we need more fungicides because we don't have this leg in place. The inducing elicitor bit, this can be other microbes. So I just mentioned how I like the idea of competitive colonization. Well, plants are out there in the heat and the drought and the cold and the acid rain and ultraviolet radiation. Those microbes don't always persist the way they do in our bodies. So I'm standing up here, and probably every one of you sees one of me. But the truth is, I'm standing up here and I'm a community of 1 trillion organisms. And I'm just reeking with New Hampshire bacteria on my eyes and my skin and my respiratory tract and my digestive tract. And if I didn't have my friends, I'd be a sitting duck. I'd be an open niche for disease. Similarly with plants. And it's going to induce a systemic response. Nutrients are going to. Herbal preparations, resveratrol and knotweed. There's a product called regalia. It's an extract of resveratrol, but it stimulates this systemic response. Using compost teas, compost extracts. Now you're getting organisms, but it's the same thing at play. Seaweed is another, humic acid extracts. So when I do what I call holistic orcharding, I call it the holistic core recipe that I'm spraying, and it's primarily seaweed and seed oils like neem and karanja, because they have lots of fatty acids, and it's microbes from effective microorganisms, and it's seaweed. And I do different things, tweak that at different points in the season. But I'm plugging into this way of how does nature induce systemic resistance to disease. The driving point here is that it's all about photosynthesis. And two ways I want to emphasize here. One is healthy plant metabolism. It all begins with that sun shining and simple sugars being produced to trade with the biology in the soil. And the other is that those simple sugars are directed down to trade with the biology, which in turn brings nutrients from that side. So, again, everything I just said, photosynthesis. How can we enhance photosynthesis? What can we do to help our plants grow better? So in the book, Mycorrhizal Planet, I articulated this idea of the non-disturbance principle. And you've heard it before, although Leopold talks about how we need to have a land ethic. We need to understand that our role as Homo sapiens is not conqueror of the land community, but just we're a plain member and citizen of that. And all species together need to collaborate, as the fungi are teaching. So I talked about begin with gratefulness. Don't screw up. How do you screw up? Tillage. So here we're in a favorable crowd. Say, good for you, the no-tilled land. Chemical disturbance has impacts on soil life. We all make choices. I use the term biological compromise. There are times, particularly when we're transitioning ground back towards a healthy direction, where we have to make even harder choices than when we start to get things better. And I tell people, just think about the biology, understand that those choices, they're okay, that you have goals. Just like me, we want to do things better. The more we learn to be better. And by being better, that's where doing fungal things comes into play. understanding when it might be relevant to inoculate, understanding that a diversity of plants is really key, having a diversity of fungi and bacteria that form this network. And all of that to me is honoring the earth. When we talk about transition, it's not an instant thing. And those of you who went to no-till systems know that year one, you saw some good, you also had some challenges. And I tell people, this picture is connections, those kind of biological connections in a grassland system that was overgrazed, and how it takes time. 1 year, 2 years, 3 years. I tell people 3 to 9 years are going to be involved, depending on the degree of degradation that land was subject to, the history of what the cropping was, and the disturbances that took place. And that's okay, because we have to go through it. We have to begin somewhere. And by beginning, we're going to get to the end point. So Bill Mollison, whose work is now known as permaculture, talked about how we must turn all our resources to repairing the natural world. You know, I just sat in on the Rafferty's talk 2 sessions ago in Western Australia, and the pictures they showed of what their land has become, not their land, they're bringing land back, but land surrounding them. The degree of degradation that clouds don't even form because there's no wild plant life, the salinity in the soils. We got to change all that worldwide. And by forming communities like no-till in the plains, and farmers connecting, older farmers sharing that experience with younger farmers telling older farmers how to do it better. It's important work, really important work. So let's talk a little bit about the farm side of this. These are soybeans in Iowa, which you probably are envious of. But no, this is actually in Hawaii, and this is the kalo plant, which they get that root, and I don't remember what, I don't have that in my notes. I don't remember. Okay, that's what I'm talking about. But that's amazing to look at. But let's start here. This notion of bacterial and fungal biomass. So again, we don't have great measures of like knowing specifically what organisms are in our soil. Some, but again, we don't know. We know maybe 10% of that. But we do have the ability to recognize the bacterial aspect from the fungal aspect. And so in a unrelenting tillage situation where the soil is broken up constantly, every year, year after year, that bacterial biomass is going to outnumber the fungal biomass by like 100 to 1. And so without the fungal piece, the need for agricultural medicines to deal with the symptoms of pests and disease just are that much more ramped up. What I call conventional no-till is where you're not doing the cover cropping piece. And you're all tuned into that. But even there, by not tilling, you start to get more fungal biomass. Some of it is mycorrhizal, some of it is sapotrophic fungi, the decomposers. And the goal is, let's get it to 1 to 1. When you start working more biologically, you're going to see that fungal biomass be more like 3 to 1. It can be higher, but again, it's all about the disturbance and your ability to bring more plant diversity onto the scene. Holistic orcharding, and this is not a scorecard, we're not rating my agriculture against yours, but perennial trees really want that fungal biomass to be 10 to 1. And that's what's found on the edge of the forest. And I stand up here, I'm not telling people, if you're going to plant fruit trees, make sure you plant them on the edge of the forest. What I'm saying is we want to bring the soil ecology found on the edge of the forest underneath our fruit trees. And when I say something like that, I'm also have the ability to think, I want to emulate what happens on the edge of the forest. You know, small trees fall over, succession species, the lignins in them are broken down. So I bring chipped wood, a small branch structure, into my orchard because that's how the right kind of soil is built for the agriculture that I do. And then if you get into the old growth forest where there's no disturbance, that fungal biomass is going to be 100 to 1 greater. So we got that concept. So cover crop cocktails, and it's really fascinating to me to sit in on like Lauren's presentation and see how different plants are mixed together and interseeding into the crop plant and all that. Again, it's all about plant diversity because that brings on microbe diversity, more players involved. A few years ago, when I spoke at the Acres Conference, Christine Jones was speaking there as well. And this was the first time that I heard of this idea of plant quorum sensing. And this, again, the message is diversity brings more players into the network. And she described this experiment that was done, I believe in South Dakota, where triticale was grown. And it turned out to be a very dry summer, and they were not irrigated. And the triticale crop by itself was going nowhere. There was not going to be a harvest. And the triticale with 1 or 2 or 3 companion plants was going nowhere. It was really dry. With 4 or 5 or 6 or 7 companion plants, it was going nowhere. It was just too dry for the plant to be healthy. But with 8 companion plants, everything was green and growing as you would desire as a grower. And it's not that it takes 8 different plants. In that combination, it worked. It's just that it takes a diversity of plants. That's what we're planting here. And probably one of the most important things that needs to take place, going back to Bill Mollison and the chance to restore degraded lands, is we can't leave fields fallow. Your principle that I'm hearing again and again is have the land in green year round. That's the most important thing that we can do, and we can accomplish that as we get more people to understand what's taking place here. But when you grow just corn for the year, or just soybeans, that's a third of the year, the 365 days, if that. And to leave that bare is to end photosynthesis for that 2/3 of the year. To not have photosynthesis is to not have active roots, is to not have active fungi forming soil aggregates, putting carbon in the soil. And just flying over in an airplane right now over the Midwest, and you look down, it's like we have a long ways to go. Our job as farmers is the flow of organic matter. And the main way we can do that is living plants, leaving stubble to decompose on the surface. That's important when restoring that organic matter. Grazing fits into this picture. And we can do more hands-on methods, as I do in my orchard or in market gardens. Making compost is great. All that's to the good. But really the main way we have is working with plants at photosynthesis. This whole notion of windbreaks and riparian buffers. There's so many ways you can create diversity. And when you have things like willows and alders in there, you have species of trees that have those ectomycorrhizal fungi reaching 12 feet, bringing those nutrients up into the protoplasm of those trees, which, because it's so-called softwood species, soft hardwood species, willow, alder, popple, soft maple, etc. They also have endo affiliations. Now it's going into the passage plants. Similarly, when you plant a conservation strip and have all kinds of beneficial diversity in a prairie strip running down your row crops or maybe the ridge or however you go about that, you're creating pockets of fungal diversity that can reach out into the row crops and restore what's taking place there. Now, it takes two to tango. This idea that it's fungus and root together. You know, in the fall, I love to plant oats and field pea and, well, late summer, and tillage radish. And all 3 of those plants winter kill in my climate. To me, this is like biological tillage, you know. I would never say no to a farming because I really love biological tillage. So I till that way with the plants and with biology. Rachel Carson said, those who contemplate the beauty of the earth find reserves of strength that will endure as long as life lasts. These are complicated times on our planet. And am really thrilled to be among farmers who are doing the kind of work that are going to change things around. The fungus root stands revealed, this whole union of plant and fungi dating back to 450 million years ago. This is a redemption song. It's a soil redemption song. It's the way forward. And I'll just end by saying, I love this comment from Grant and Don Bright Fruits up in Minnesota. Farming is fun again. This is so fun to learn this stuff. See each year the 40, 50 chances we get to figure it out in our basically short lifetimes. That's great. Thank you.